All right. Um, Good afternoon, good evening, good morning. So welcome to week 5 of FEA, Finite Element Analysis. You guys are on the final week. Um, I'm gonna skip the attendance real quick while I start talking. So for those of you who've completed weeks 1 and 2 assignments, you probably didn't get an email from me. But for those of you who have not done them yet, or by I think it was Saturday or Sunday, if I had not gotten your submission yet, you should have gotten an email. Again, it's due July 20th, all your tasks. So week 1, week 2, and week 5, they're all due July 20th, and I'm not gonna grant any extension. So be sure you get those done. Again, something that I really want to stress is week 5 assignments are mandatory. So even though weeks 3 and 4 are optional, you will need one of the two. You will need to watch one of the two to actually do week 5's assignment. So it's your choice. But yeah, that's what I wanted to let you guys know. I'll be holding my last office hours this Saturday from 2 to 4. So 2 hours just to make sure, if you guys have any questions regarding weeks 1 or 2, 3, 4, or 5, any of the assignments, I'll be there on Zoom, and you could hop on over and ask me any questions. So besides that, I've also gotten a few questions regarding grading and sort of how this grading spectrum sort of works. So if you guys submitted something for weeks 1, 2, and 5, I won't really check if it's right or wrong. If I see that you set it up right, you're able to get results that somewhat make sense, then you guys are gonna pass. Regarding feedback, I am gonna be releasing feedback. I can't give you any promises, but it should come between July 21 up until the week after that. So the Friday after that, you should get comments between those dates. If you don't, please do reach out to me, but I will try my best to get it done between those dates. And that's when I'll be sort of letting you guys know if you guys might have did something wrong with your analysis, or if there's some discrepancies with what I have with and what you have. But again, there's a lot of factors that come into play with FEA. So the slightest difference in how we set up our studies could mean different results. Although it might not be great in magnitude, it might still be different. So I don't think it's a good idea for me personally to just compare my study with your study and see if we have the same magnitudes of stress, displacement. That's not going to work. But what I will be trying to see is whether or not the magnitude is close. Let's say if my displacement is to a factor of -4, and your displacement is like to the factor of 5 or something, right? That's a huge difference. Then I'll sort of hit you up, put down a comment and ask you what's happening here. I might look at your work, look at your loads, see if you guys did something wrong. But if it's still within a factor of say -4, -3, then it's fine, right? It's similar. It's not the same, but it's similar, and I'll take that. But yeah, so weeks 3 and 4 again are optional. You guys can submit, or you just don't. If you do submit, I'll be sure to put down some feedback, so you guys know what you're doing right or what you're doing wrong. But yeah, I've been looking at the submission forms. I want to thank you guys for the feedback. It means a lot. This is my first time teaching the course like individually. Back in spring, I was not an instructor. I was just a TA, so I was just helping. So yeah, this helps me a lot. And going forward, your feedback means a lot to me because I'll be building off that for fall semester and spring semester and semesters to come. But yeah, without further ado, let's get to module 5. Cool. So before we get to anything, I just wanted to sort of wrap the course up and sort of give you an idea of what you've learned throughout these 5 weeks. So maybe if you want to add this to your resume or LinkedIn, right? You want a clear picture of what exactly you've learned within these 5 weeks. Here it is. Of course, first weeks, we were looking at static stress simulation, which is the most simple part of FEA. And what we learned throughout the first 2 weeks were, of course, go from the design to simulation interface on Fusion 360. That was basic. But then you guys also learned how to apply materials, create new nonlinear materials. If you guys don't remember that, go back to lecture 1 because we did briefly talk about that. If you guys want to learn more about that, feel free to email me shoot me a Slack or come to office hours and we could discuss sort of how to run simulations on nonlinear materials, but that's something you guys learn. Second is also applying constraints and loads. I know if you look at Fusion's interface for constraints, at the very least, you have fixed and pinned, and I think there was another one, but we've always been using fixed. Again, this is an introductory course, so if you guys want to take a look at how a pin constraint would work, please feel free to do that. As well as loads, we've been just looking at loads. There are pressure, for example, we could apply moments to our model, but we weren't able to touch on that. But hopefully with the knowledge you have now and sort of being able to apply loads to your model, you guys can sort of build off that. Say you want to apply, like what I did with the example of the Titan submersible, you could apply pressure now, for instance. And yeah, hopefully it carries over in the future when you're doing FEA on your own. Next is, of course, one of the most important parts of FEA, which is meshing. More specifically, what we did is we took a look at different meshing options and sort of what makes them different, what each of their purposes are, and sort of when and where to use them, the ups and downs of messing with the mesh settings. Then we took a look at shape optimization, how that can help in sort of making your model more efficient, as well as just making your model cheaper, making sure that you're keeping that safety factor to a level that is acceptable, yet not dangerous to a level where your model will break. And of course, analyzing results, which we've been doing throughout these past 4 weeks. Week 3, a bit shorter now, we looked at structural buckling. I put down the key components down into 3 bullet forms. Of course, first is taking a look at how we could use the buckling load factor in our results to figure out what the critical buckling force is for that specific design, right? Next, we took a look at different buckling load factors. And if you don't remember what this was sort of the table I showed in one of the slides, where it gave a range of buckling load factors and the corresponding results. Like if buckling load factor is greater than 1, then you should expect buckling. If it's 1 or between 0 and 1, then you should expect buckling to occur. If it's negative, and all of that, right? We took a look at that. And lastly, we took a look at the concept of modes. Again, this is like when you're setting up your buckling stress analysis, it sort of asks how many modes you'd want. In this case, week 3, we did 3 modes. So again, what that means is just now Fusion's going to run 3 different cases of your force acting on your model. Because again, there are a lot of different ways that your load could be acting on the model. I go through a lot more on week 3's lecture. So gonna touch up on that, please do. It's there on YouTube, and after this course is over, you can still refer to that through on ASME's YouTube, because I'm not going to be deleting that. But yeah, next thing is what we did last week, dynamic event simulation. Again, this one's a lot more complicated than the first 3 weeks we've done, because there's a lot more to take into account. More specifically with dynamic event simulation, it's a bit more complicated because now you could be dealing with more than one model, more than one part. And because of that, there's a lot more that you have to define and let Fusion know. But here are a couple things that we touched on last week, and hopefully these are now things you sort of understand at the very least. First is, of course, dynamic constraints and loads, how this is different from just your normal constraints and loads. Again, with the dynamic loads, you have now initial linear velocity, whereas in your static stress analysis, we didn't really take a look at that, and that wasn't really a big thing in static stress analysis. Next is, of course, element deletion criteria. This is sort of what makes dynamic event simulation a lot more fun, where you actually get to see things breaking and things deforming based on the simulation you're trying to do, based on the load you're applying on your model, right? So fun stuff. Next, of course, is the application of a rigid body. A good example of this that I wasn't able to say last week is say you're shooting a bullet to the ground, and you'd like to simulate that ground, right? Like let's say you have a concrete ground, just a ground, just normal ground. It'd be very inefficient if you tried to model that the ground itself, because I mean, I don't think you can, because it spans like a long way. But what you can do instead is what I did, create a cube there and just make it rigid if you'd like, because then again, remember, rigid means that there's no vibration, there's no movement, and there won't be any deformation with our body. So if you'd like to sort of simulate sort of what will happen, like shooting a bullet to the ground, you could make that block rigid to sort of take the place of the ground, right? Next is using prescribed translation. And this is the graph that you saw, the multiplier curve. This sort of helps you model your simulation a lot more accurately. What this is, again, if you want a more detailed explanation, you can go back to week 4. I'm just going to summarize things up. Like with the bullet example, for example, we know for a fact that when we shoot a bullet, it won't reach its terminal velocity immediately. It's going to accelerate through the air, and prescribed translation, as well as the multiplier curve, allows us to sort of mess around and sort of tell Fusion, like, this is how much I want the bullet to accelerate. And, within the span of time that I have prescribed, I want my bullet to reach its terminal velocity at a specific time before, and just keep it as a terminal velocity. Same way, say if you're trying to simulate a plate dropping to the ground, we know for a fact that maybe the plate's terminal velocity is like 30 centimeters per second, or something like that. We know for a fact that when we first let go of the plate, it's not going to be 30 centimeters per second, right? It might start 0, and then 2, 4, 5, 6, and it's going to keep accelerating. Prescribed translation, as well as the multiplier curve, allows us to, tell Fusion how our plate or our object's going to be moving. And lastly, of course, is the usage of contacts. This is what gave us an issue last week. But the usage of contacts actually allows us to tell Fusion that something's going to happen between bodies, which we never had to deal with on weeks 1, 2, and 3, because we're looking at an individual model. But on week 4, we had 3 different models, so we had to define contacts. So Fusion knows that our bodies are going to interact with each other. But yeah, that's what we learned in the past 4 weeks. Now, week 5 is going to be based on these 2 now. And again, it's one of the 2. I'll talk more about it later. If you guys sort of forgot how to create a study of buckling stress or a dynamic event simulation, I'm going to briefly go through it right now. If you guys haven't watched week 3 or week 4 lectures, I really suggest you guys watch those instead of this, because this will be super vague, super general, while weeks 3 and 4 I really got into it. But yeah, let's move on to the project. I've gotten a couple questions about what exactly entails the project, what do you guys need to do. So yeah, let me go over it, sort of let you guys know what I'm expecting from the project. So I want you guys to create a structural buckling simulation or a dynamic event simulation. You pick one. I don't really, doesn't really matter which one you pick, but please do pick one. And of course, when you're designing it, this is a no-brainer, but you should have a 3D object. And with the extrusion rule, I just want a 3D object. So if you guys decide to use the revolve tool or the loft tool, that's fine. That's fine, as long as you have a 3D object. You guys are hitting the benchmark. And here are the settings that I want you guys to have for buckling. I want you to have at least 3 modes. You guys can sort of mess around, see what happens if you have 6, 7 modes. But that's not required. I'm asking just a minimum of 3. And for dynamic event simulation, there are 2 main components that you guys might need to change. First is the total duration. Last week, we had it at 0.001 seconds. You guys can choose to go over that or stay at 0.001 seconds, but please don't go below that. And for your results interval, 12 is fine. You can go higher, of course, but minimum of 12 for me should be good. Before I continue, do you guys have any questions regarding the final project requirements? For those of you here, again, if you're watching this recording, send me a message on Slack or send me an email. Okay. Looks like there's none from now. If you guys are chatting, just continue to do that. Please do. Okay, I got a chat actually. Okay, sorry. So if you guys do chat, please chat to everyone because I have my iPad here right next to me, and this is where I'll be seeing all my messages. Not on my laptop where I'm screen sharing. But yeah, basically, again, I want you guys to model something yourself. So this is when sort of prior experience of CAD will come in useful. So you will need to use that knowledge of CAD to create something, a part, an assembly, whatever that may be, and bring that to the simulation workspace, right? Like you did on week two's project, basically. Yeah. And here's what I want from your submission. Again, same format as the past weeks. Screenshots in a Google document, save as PDF, and submitted through the Google Forms. If you guys choose the structural buckling analysis to do, you will need 2 screenshots, one of the meshed model with loads and constraints visible. So again, this is before you finish your simulation. This is before you hit solve. I want to see what you guys are doing with the loads and constraints, what you guys are doing with your model, as well as what your model is exactly. And second, of course, of your results. And I want your deformation tab to be switched to adjusted, just because then I would actually be able to see some deformation happening. Because if you keep it as actual, you know, it might be a relatively small change. I just want to see what would happen in a adjusted deformation. But that's it for structural buckling. Next one is dynamic event simulation. I wouldn't say it's a lot. It's a bit more tricky. It just depends on what you guys want to do. Personally, for me, I find dynamic event simulation a lot more fun to simulate, a lot more fun to create, though it takes longer for sure. But yeah, if you guys choose the dynamic event simulation, I will ask you guys to submit 3 screenshots in one Google Docs. These 3 screenshots should entail one of your model with loads and constraints visible, similar to this first one. Before you hit solve, I just want to see what you're trying to do with your study. Okay. Okay, I see someone is asking here for buffering. How do you show the different modes? Are you asking once you solve the studies and you're trying to look at it from the results? And these screenshots. Okay, for buckling, I'm just asking you guys to submit one mode. You could do this. I'm gonna swipe real quick to Fusion and show you guys what you could do if you want to show all 3. Go to results here. One thing you could do is just click down here and send a screenshot like that, so I could see what value all your modes are. But I'm not requiring you guys to sort of go one by one and sending me screenshots of each sort of deformation. So just give me buckling mode 1, 2, 3, or whichever one you want. But click this drop down so I could see the values here. Does that make sense? So cool. All right. Yeah, please do keep dropping questions in the chat if you do have any questions regarding the task. But yeah, okay. So for dynamic event simulation, one of the model before you solve it. The second one would be of your simulation at step 0. So this case, everything should probably be blue because there shouldn't be any contact. But if you do start your simulation where contact is happening, that's fine as well. Just one of the simulation at step 0 and one at the final step. And I didn't put in a numerical value here because again, let me go back. This is completely up to you guys. You guys can choose 12 or more. Just send me a screenshot of that final step. So yeah, that's 3 in total. You know, compress them, adjusted. Okay. Yeah. So like this. Wait, yeah. So I want you guys to have it in adjusted, so I could sort of see what exactly would happen. Because again, if I put it in undeformed here, really, I can't tell. Okay. Yeah. So basically, just switch your deformation here. Make sure it's on adjusted instead of undeformed when you submit your screenshots. So, okay. So ideally, here is an example of what I want the screenshot to look like. So here, okay, everything's good. Now I would just screenshot this page and and just compile it on a Google Docs, basically. So, sorry. Okay, actually, that will be it. One last thing is, again, model for the dynamic event simulation can be meshed or unmeshed. I don't really care. So if you guys accidentally, screenshot it before generating your mesh, this first one, that's fine. You don't have to take another screenshot. Just compile that on the Google Docs. But yeah, before we get going, so after this, I'm going to give everyone here on the Zoom about 30 minutes, 40 minutes to start working on their projects. Before that, do you guys have any more questions? Okay. All right. Okay, I'll take that as a no. Before I pause the recording, I realize some students watch the recording might not have the copy of the chat. So I'm just gonna read the chat, the questions that appeared in chat, and sort of explain how to go through it again. So the first question is for buckling, how we show the different modes in the screenshot. So you would click on this drop down here where it says buckling mode 1. And this will show you all the different buckling modes, all the different buckling load factors based on each mode here. So that's how you would do the screenshot. So it'll look like this for buckling, screenshot there. And the second question that was asked is, what does adjusted mean in the buckling result? So again, coming back, I said here the submission requirements is one screenshot of your result, and it should be adjusted. So the answer to that question is up here in your deformation tab. You guys can pick here, just pick adjusted here because based on how you set up Fusion, you might have on default just undeformed. I want you guys to switch over to adjusted here. If you guys do decide to do adjusted 0.5, adjusted 2, adjusted 5, it's fine. But as I just want to see it adjusted, right? I don't want to see it undeformed. But yeah, that's all the questions I got from the chat. For those of you watching the recording, I will pause the recording here. We'll continue in about 25 to 30 minutes. So yeah, okay. Okay, we're gonna go back to the slides now. Cool. Okay, so now that you are, hold up, let me just make sure that I'm recording. Okay, cool, should be good. So now that you've learned how to set up a static stress simulation, a buckling stress simulation, a dynamic event simulation, what do you do now, right? What's there to what's there to do now with all that knowledge, right? There's a couple things you could do, of course. First thing that comes to mind is sort of move on more complex and more commonly used industry software for FEA. First being ANSYS Workbench. Now, this is one that you can actually go to from Fusion itself. I'm gonna swipe real quick to show you what I mean. Here, you could simply just bring whatever you have on Fusion to ANSYS from Fusion itself, from here, of course, right? Next one you could do is SolidWorks simulation. Now, I'm not sure if you guys do know, but so ANSYS is a standalone software, whereas SolidWorks simulation is under the big company Dassault that also created SolidWorks. So, if you modeled something through SolidWorks, it would probably be best if you could do FEA on SolidWorks simulation because your files would be compatible and it's a lot easier to import a SolidWorks file from SolidWorks itself to SolidWorks simulation because simulation would be just another add-in. One thing I forgot to mention, ANSYS Workbench is free for students. If you go search up on Google ANSYS student, first link should be like an ANSYS student download where you could download ANSYS for free and sort of mess around with that. Second one, SolidWorks simulation is also free for students. And this one is because Purdue allows their students to download SolidWorks for free. I'm sure if you search up just like Purdue SolidWorks download, it should come up. If you're a Purdue student, it should be free, and you can pick what add-ons you want along with SolidWorks, and one of them being SolidWorks simulation. Next one is Star CCM. This one is under the same branch as NX under Siemens. So if you guys took CGT 163, this would be the FEA software you'd want to use, say, if you were curious on how your models would do back from CGT 163, right? The issue is with this is I'm not sure if Purdue students have access to Star CCM. Maybe you could try accessing it from Apps Anywhere, but I can't guarantee you that it'll work. And of course, there are a lot more out there. The three I listed down here are the most commonly used in industry, as well as probably the ones that are most used within Purdue, within like different clubs at Purdue, different organizations, research. These three are probably the most common. One thing to note is with SolidWorks, Star CCM, there's more you can do than just FEA. A lot of these sort of softwares combine FEA and CFD, computational fluid dynamics. So if you'd like to test more so the aerodynamics of a model you've created, you know, SolidWorks also has that. It's called SolidWorks Flow Simulation for SolidWorks, and Star CCM also just has a CFD module if you'd like to sort of look into that. But again, as I said, I can't guarantee you that Star CCM is available for Purdue students for free. But yeah, another thing you could do with your FEA knowledge now is join a club and work on a specific sub-theme. What do I mean by that, right? Say you work for an SAE team, right? Say the Formula team, the Purdue Electric Racing Team, Solar Racing, Baja, right? They're going to need students who are able to run FEA to see, say, if their suspensions will work and all that goodies, right? Now, with the ability to set up your studies, right, it becomes a lot more advantageous. You'll have sort of the higher ground over other students who haven't taken the course, who might not know how to work on FEA software, because now you know, like, okay, I have assigned my materials, I've meshed my model. What else am I missing? Okay, I need to apply constraints now, and then I need to apply the right load, right? So you guys sort of have that checklist in the back of your head already to sort of prepare an FEA study well enough, right? Of course, other things you could do, mess around with Fusion's FEA, because we've like just touched on Fusion's capabilities, right? Like for example, on static stress analysis, instead of having one part, why not have, say, an assembly, right? That will require you to apply contacts, you know, maybe define your constraints a bit different, add more forces. Same way with buckling stress analysis. Say you'd like to make a table. Well, now it becomes a lot more complicated, because then you'd have to constrain each leg to make sure they all sort of work in a different way. They could deform in different manners. But stuff like that, really, you could do now, hopefully, now that you've gone through these past 5 weeks and these 5 assignments, right? But yeah, that is it for me. Thank you for sticking around 5 weeks. You guys been great. Again, submit weeks 1, 2, 2, and 5 before July 20th, because I will not be granting any extension after that. Though I will send you guys a reminder this coming Sunday, and maybe on the Tuesday or Wednesday, if I see that you have not submitted your work yet. But if you have any other questions, please do reach out to me on Slack or through email. Even if the class is over, maybe come fall semester, if you guys have any questions, just reach out to me. I'll be here. But yeah, thank you guys so much for sticking around 5 weeks. Here is the submission link. I will also be posting it on Slack. I'll give you guys a few minutes. Cool. And yeah, thank you. That has been it for me. From ASME, and Milestones, I want to say thank you for enrolling in a course. Hopefully you guys found this educational. Hopefully you guys learned something. And yeah, if you guys want to learn more about it or are interested in FEA, I know ME has a course on FEA. So please do take a look at that if that's something you're interested in. But yeah, thank you guys so much. Hopefully you guys have a good rest of your summer.